Microwave bench frequency measurements series on microwave engineering, lecture number 6.14. Frequency is an important parameter, a significant aspect of electromagnetic wave. Its importance, its significance arises from the fact that waves behavior changes with the frequency. Behavior of a wave whose frequency is in HF band is different from the behavior of a wave whose frequency is in VHF. When frequency is very high, falling in light band, the wave behaves like light. Even in light also, one frequency wave behaves like green, another frequency behaves like red. Both are electromagnetic waves. Only frequency differs, behavior also differing. So it is the frequency which makes the wave behavior differ at different frequencies. The lower frequencies are measured with frequency meters or using bridge circuits, but the same measuring instruments, measuring setups, they are not useful when frequency of the wave is in megahertz or in gigahertz. To measure microwaves, their frequencies, bench setup has been used. If the bench is made to work for X band, then it can measure the frequencies that fall in the X band only. If it is made to work for S band frequencies, then the bench can measure frequencies that fall in the S band only. However, a bench can be made to measure frequencies that fall above or below the band for which the bench is made by converting those frequencies into the band for which the bench is made. Suppose the bench is made to work for X band. To measure a frequency that is above X band, first it has to be down converted by a certain amount, by certain factor, so that the frequency now is in the X band. Using bench, the frequency can be measured. The measured value has to be then up converted by the amount by which it was down converted in the beginning. By following similar procedure, one can measure frequencies which are below S band 2. First, they are to be up converted by certain fixed amount so that now the wave is in X band. After measuring the frequency, the measured value has to be down converted by an amount by which it was up converted initially. In the present session, our focus is on measuring wave frequencies with microwave bench. Basically, there are two techniques. One is called direct, another is with slotted section or slotted section method. Direct method measures frequency using wave meter. It is also called dip method. The second method, slotted line method or slotted section method, it measures frequency via cutoff wavelength and guide wavelength. Now we move to the core session where these two methods are described in detail. A few introductory remarks for the session. Frequency with bench. Frequency is an important parameter in any communication system, more so for microwave communication system. As microwaves are higher frequencies, the methods or instruments used for low frequencies are not suitable to measure microwave frequencies. Two methods by which the frequency is measured in the laboratory are available. One is direct method. It uses wave meter and hence it can be used only when the wave meter is available. Direct method is possible only when wave meter is on hand. The second one is indirect method. It requires the measurement of guide wavelength and also cutoff wavelength. Direct method is known as dip method. It is also known as wave meter method. Wave meter is inserted into the bench with the flap attenuator on one side and waveguide detector on the other side. The output of the waveguide detector is given to VSWR meter, and the power flow in the bench is adjusted until proper deflection is observed in the VSWR meter. These are all preliminary arrangements, preliminary adjustments. After all the necessary adjustments done, the wave meter is rotated until it is on one end of the scale. The indication of the meter must be either 12 or 8. Notice, instead of waveguide detector, one can use a matched terminated standing wave detector also in the bench setup. In such case, the output of the tunable probe must be connected to VSWR. Either one can be used. Either waveguide detector or standing wave detector can work here. Then the wave meter is rotated in the opposite direction slowly but continuously by pressing its cap with the center finger of the left hand, while observing the deflection in the VSWR meter simultaneously. Rotation of the meter and observation of the deflection in VSWR meter. Both must be done simultaneously. One is done with finger, another is done with eyes. At one point of time, while the wave meter is being rotated, a fall or dip in the deflection of VSWR meter can be noticed. You are rotating the wave meter with the center finger slowly and continuously while observing the deflection in VSWR meter simultaneously. When this activity is being continued, at one point of time, one can notice a fall in the deflection of VSWR meter indication. Then the rotation of the wave meter is to be stopped, and indication of the meter in between rings against the pointer is to be noted down. This is the frequency of the wave that is running in the bench. The wave meter here has 8 on the lower side or 8.2 on the lower side, 12.4 on the upper side. Therefore, it can be used to measure only frequencies in between 8.2 and 12.4 gigahertz, that is X band. Frequencies falling below it or above X band, they cannot be measured directly by this wave meter. Of course, after upgrading or downgrading, up converting or down converting, the frequency of the wave can be brought into the X band, and then the wave meter can be used to measure the frequency. Now we move to second method, indirect method. This method is called slotted line method. There is a formula behind the design of this method. The guide wavelength, cutoff wavelength, these two are related to wavelength, ordinary wavelength. The relation is 1 by lambda g square plus 1 by lambda c square is equal to 1 by lambda naught square. This is the formula. Using bench, we measure lambda g. With the help of a scale, one can find lambda c. When these two are available, lambda naught can be calculated. From lambda naught, frequency can be obtained using formula V by lambda naught is equal to frequency. This is the mathematics behind this particular measurement technique. The bench setup is shown here. Notice here, bench is used to measure guide wavelength. Only for the measurement of guide wavelength, bench is required. Here, in this method, the bench setup for measuring guide wavelength is shown here. Source, supply, source. Source may be reflex klystron or gun oscillator. Source supply belongs to the source. Source is followed by isolator and flap attenuator. Then one can place frequency meter or wave meter after attenuator. It is optional, but its presence is useful to do a cross check. Slotted line method gives frequency of the wave. Frequency meter or wave meter, whatever is there in the circuit in the bench, it also gives frequency of the wave. To confirm the correctness of the frequency given by slotted line method, the frequency given by frequency meter or wave meter becomes useful. So for cross-check purpose, presence of frequency meter is useful. Otherwise, it is not essential in carrying out slotted line method. Then, standing wave detector terminated with a short. Output of the tunable probe is given to VSWR meter. All this is meant for measuring guide wavelength. Short reflects entire incident wave. Now we have two strong waves in the standing wave in the slotted line section. It results in an almost pure standing wave pattern. Pure standing wave pattern means the one with its voltage minimum points at zero. This pattern appears like this. The distance between two consecutive minimum points, it is equal to lambda g by 2. Distance between two consecutive maxima also lambda g by 2, but while doing measurements with bench, we use minima, not maxima. The reason is going to be explained soon in the present session itself. So using standing wave detector, the distance between two consecutive minima, it is found, and when it is multiplied by 2, we will be getting guide wavelength. Taking a scale and measuring the distance between side walls, inner distance between the side walls, one can have A. If you multiply A with 2, 2A is equal to cutoff wavelength. It is because the wave that is used in the bench is a dominant mode wave. In case of dominant mode wave, cutoff wavelength is twice the distance between the side walls. As mode of the wave in the bench is dominant, the cutoff wavelength lambda c is equal to twice the inner distance between the side walls of the waveguide. By measuring this distance with a long scale, multiplying it with 2, cutoff wavelength can be obtained. To find the guide wavelength, lambda g, terminate the bench with a short. It results in the formation of standing wave pattern in the slotted section. The output of the tunable probe is given to VSWR meter, and the distance between the two consecutive minima is measured using Vernier scale provided. Twice this amount gives guide wave. Once guide wavelength, once cutoff wavelength, both are available, then lambda naught can be determined. Once lambda naught is determined, found, frequency can be computed within no time. An aspect to note is regarding the unusability of the locations of the maxima in measuring guide wavelength. Even though the distance between consecutive maxima like minima is also lambda g by 2. See, this is standing wave pattern. The distance between two consecutive maxima is lambda g by 2. Between minima, two minima also it is lambda by g by 2. But in measuring lambda g, we try to find out the distance between two consecutive minima. We never go to find the distance between maxima. What is the reason? There is a reason. The reason for their unsuitability is a large spread of maxima when compared to minima. Because of this spread, it is difficult to locate exact maximum point. See, the spread is more. Which is the real maximum point? Is it this? Is it this? Is it this? Is it this? Difficult. But the spread of minima is very short when compared to maximum. So location of minima can be determined exactly and more easily. For this reason, it is always preferred minima while making measurements to find guide wavelength. Because of these reasons, while measuring guide wavelength, the termination is always short and it is always measured from the distance between minima locations. Here he is telling another important point. Termination should always be a short whenever we want to measure guide wavelength. The reason is short minima happens when the termination is open circuit or short circuit. Of course, in case of reactive, pure reactive termination also, the minima can be short. Out of these three types of terminations, easily available one is short. Open you cannot have. Simply opening the outer port of standing wave detector cannot be a open circuit. At open circuit, you can notice there exists radiation. Something is going out. When something is going out, how can it be a open circuit? Open circuit is one which reflects back towards the source the entire incident wave. Here, radiation, it is going out. Therefore, simply physically opening the port of standing wave detector into space cannot be open circuit. So there is difficulty in implementing open circuit. Therefore, we don't opt for open circuit. Similarly, connecting reactive load, purely reactive, that is also somewhat difficult process when compared to terminating the detector with a shorting plate. Shorting or short circuit is the one that is simplest out of all the three possibilities. So, when it is a short, reflected wave is as strong as incident wave. Interference between them leads to highly sharp minimum points. As they are sharper, easy, it becomes quite easy to locate them. It becomes easy to get accurate distance between two minimum points. So guide wavelength is somewhat exact and accurate. So here the point is while measuring guide wavelength, the termination is always short and measuring points are always minima points. Precaution. In both the methods, while performing the experiment, the source should remain undisturbed, giving out the same frequency wave until completion of the measurement. For better accuracy, distances between several successive minima may be noted and their average be considered to calculate the guide wavelength. Before going further, one point is required to be mentioned. The length of the standing wave detector, it is such that it can have only three minima, maybe like this, at the highest frequency of operation. If we assume the frequency is somewhere in the middle of the band, then in such case there may be 4 or 5 minima, like this. 1, 2, 3, 4, 5 minima. So one can measure the location. One can measure the location of second minimum, third, fourth, the distance between them. This gives 1 lambda g by 2. This gives another lambda g by 2. This gives another lambda g by 2. This gives another lambda g by 2. Average them and multiply it with 2. It gives guide wavelength. These are the points, these are the aspects which I want to share with you regarding frequency measurements with bench for right now. To recap, measurement of frequency with wave meter. It is also called dip method or direct method. It was described, and then slotted line method. It was explained in detail. Hope you have a wonderful, beautiful, transforming and enriching learning experience. We meet again soon in another session. See you. Bye bye.